Welcome to video e-learning program. In this session, I'll be discussing about the applications of the linked list. There are two applications that we will be discussing. Number one is called as the polynomial addition, or how to represent a polynomial using a linked list. The second application is nothing but the sparse matrix. So I will discuss about the sparse matrix in the next video. Now, as far as the polynomial addition is concerned, now we will be representing a polynomial using a singly linked list. Then we will show how this could be used in order to add two polynomials of any length. Number of terms could be any. And also towards the end of my lecture, we're demonstrating the working of this in C language using Visual Code 2019. So let me just share the PPT. So this is called as polynomial addition, but to start with, we should know how to represent a polynomial using a linked list. Now, why we are using a linked list to represent or to implement this polynomial addition or any other operation on the polynomials is the fact that a given polynomial, we will not know in advance how many terms are there. So it is a good idea to use a linked list for this purpose. For instance, one polynomial may have 3 terms and another polynomial may have 10 terms. Now, how can we find out in advance that how many terms are there? So as and when we get the terms, we can add nodes, and towards the end of the final term, we can just inform to the program or the algorithm in such a way that this is the end or the last term, so that we can wind up that, and the reading of this polynomial becomes so easy by using this method. And once we represent the polynomial using this linked list approach, then we can do any kind of mathematical operation. So in this case of our example, we just show only the addition. However, the listeners can actually use this technique for doing any related work with the polynomials. So let's now move on to the way in which the polynomials are represented as linked lists. Now here you can see that there are two polynomials which are specified. One A, another one is B. You can see here that the first polynomial, that is A, has got 3 terms, whereas the second polynomial, that is B, has got 5 terms. So this is what I mentioned earlier, that we do not know in advance how many how many terms will be there in each polynomial. So as and when we try to get the terms, we can actually create dynamically the nodes for the linked list and keep attaching. Secondly, we will also use a header node here and a circular linked list. So the header node here, you can see that is having an exponent term with -1. So my term here for the polynomial, has 2 info fields. It has 2 info fields. The first one is this, the second one is this. This is our next field as usual. So what is this first compartment or the first field? It represents the coefficient. You can see here the first term of A, now 5, which is the coefficient of the first term in A. The second info field is nothing but the exponent, that is 3. So 3 is your second info field. The first one is the coefficient. Similarly, the second node consists of the second term where 11 is the coefficient and 2 is the exponent. And the last term, the constant term, where the coefficient is 7 and the exponent is x power 0, which is nothing but 0. And you can see the last node's next field actually points to the header node. So here we have the terms of any polynomial. Each term actually represents a node in the linked list. Okay, so this is very convenient form of representing any polynomial using a circular linked list with a header node. And next we have the second polynomial, which is B, which is also represented in the similar fashion, where I have 5 terms. So 1, 2, 3, 4, 5. You can see the 5 nodes are there, and the last node, next field, is actually pointing to the header node of B. So now we have successfully represented the two polynomials A and B in the form of a circular linked list. Right, now we shall move on to how we could actually design the structure for a node in this particular polynomial. Okay, I would call this as polylist as the name of the structure. So I'm going to use C code here. So directly we can use later on the C program also, which you can easily understand. So as I said earlier, there are two info fields. One is your coefficient, the other one is the exponent. And we have, as usual, the next field, which is nothing but structure polylist link. So link field is my next field. Right. Then I have my type def, where node is going to be in this case for each node. So this is a self-referential structure, which is similar to our usual linked list. So any linked list, we actually have normally one info field and a link field or a next field. But in this case, we have two info fields. One is the coefficient, another one is the exponent. So obviously we have this structure defined and the type def also. So each node now consists of two info and one link field. Right. Now we will move on to the how to actually build a polynomial. That means how to read in the terms so that we can completely get our polynomial built. So that's very, and remember that this header node, the exponent field is -1 and the coefficient field is immaterial. So we could because why we have this kind of thing is that the header node should have a totally a different kind of data value compared to this. So we are not trying to get the exponent being negative for our normal terms, and hence only the header node will have this. So this is different from the normal data which is present in the given polynomial. Right, now how do we read now the polynomial? So here we have named it as read C polynomial, and this is my input parameter. That means the argument which will actually return back the modified, that means read polynomial, back to the calling program. Right. So first we have to create the header node. And this header node will have the exponent -1 and the coefficient immaterial. You can put -1 even for that, it doesn't matter, but currently it will have junk value. So the first and foremost job is to allocate dynamically the memory for this P. So that I am going to use a small macro here because that will be faster, or we can also use the normal method of P equals, bracket node, then size of struct, all that. So any method is okay. So this is a faster way of, getting our malloc being allocated for our pointer variable called P. Right. So now the first one is exponent is put as -1 and the link field is pointing to P. So that means that my P is allocated and now I have this exponent field is put as -1 and the link field is actually pointing to P again. So it's a circular one. So my header node is created with P pointing to that and my link field actually points back to the P. So that's what it happens here. So once the header node is created, then I can actually read in all the terms and keep adding that to this header node. How do we do that? So that's very simple. First, we read in the value of coefficient and exponent. You can see here scanner. Coefficient and exponent is read. And if the exponent is -1, I will not read any more terms. So this is a condition which will help us to terminate the reading of this. Okay, and we can attach any new node to this existing header node. So now I have my function called attach where I will be sending this coefficient. I'll also be sending my exponent and this P. So this function actually attaches the new node with the header node because P is now header node. So new node will be attached and it will return the updated value of that particular linked list. Then again this while loop will be executed and I will be reading in the next term, etc. until my exponent is given as -1. Okay, so that is how it's going to be carried out. So now we have to design this attach function. So now how do we design this attach function? That is very simple again, that since we have this, now we create a new node here and again put this coefficient and exponent and make sure that the header node is attached here and the next or the link field of this again should point to this. So this is the usual method which we will follow, but anyway we will see how this could be carried out. So my next slide will actually show the function called attach. Yeah, so this is the slide which shows. So when you come here, my P will have the header node, something like this. So this is my -1. This is my P. So this is a circular list. So this is my P. Okay. Now my new node temp will be allocated in order to attach. Now temp is here now. Now this is my temp. Okay, now I put this coefficient and exponent. Coefficient and exponent. So that is put already. Temp of coefficient is C and temp of exponent is E. And if P equals P of link, that means it's the first node or first term which is being added to this header node, then what I do is P of link, that is this one, I'll just attach here. So this is this one and it will put temp of link to P. So this is so this is gone anyway because we have already modified this. Link field is now pointing to this. This becomes the first term and the link field of temp will point to P. So that's done. And now last, this is another interesting you know, terminology or the method being used here. I'll also use one more pointer variable called last, which is the global variable. So which will actually point to the last node being added at any point of time. Why? Because supposing next time if I want to add one more node, let's say, so this is my new node temp. Now what I can do is actually I can simply say the link field of last, that is last of link pointing to this, and link field of this temp now can point to P. So I don't need to actually traverse through the entire list. Supposing if I have many nodes or many terms, then in order to reach to the last one, I need to actually browse through the entire list. Now, instead of doing that, I can actually do one simple operation of link field of last pointing to this current node being added and the last field pointing to this. So these two statements are more than enough in order to add any new node. So that's exactly what we'll be doing even when this attach function executes for the third one. So you can see here temp is created, and if p equals p of link, no, it's not, it's true. So it is false. So when you come here, last of link, you can see here will point to temp, and temp of link will point to p. So it's done. That is last of link pointing to temp and link of temp will be pointing. So this is my new temp. See, don't forget that blue color indicates that the next term. When P is not equal to P of link. So I have already one node added or one term added. So obviously now I have my second term in which I can take this last always pointing to this. Link of last pointing to temp and temp of link pointing to P. So it works still whatever be the number. So let me just put one more term here so that it becomes easier to. So this is my header node. So P is pointing to this. Assume that I have already added two terms. So we have this first term and the second term, and so this is my first term, this is my second term, and this is what it is pointing to the header node. So I'll just try to show you how we could add the third. So last is pointing here. And now I'll add this third term pointed by temp. So we can show easily that is this true? No, and hence I'll execute this. That is last of link should point to temp and temp of link should point to P. So temp of link pointing to P, and last is no longer this. Actually, this is my last. So this has to be updated like this. So now you can see this is the header node. Then I have first term, second term, and the third term. So that is done easily with the attach function. So what happens every time when this loop is executed, I read in the new values for the coefficient and the exponent and try to call this function attach, in which case this is getting attached as the last term to the existing circular list, and the updated value of P is available to me and I return to the column. So basically what we have done here we have written or created a polynomial with so many terms. Now this could be like two polynomials, so I can read first by using the same function, and we'll see how we could add. Right, so this is attached. Now how to add two polynomials? So let us see the concept first and then to the programming statement. Okay, now we have two polynomials here in the mathematical form. Now how do we add these two? Now we can add these two very easily by picking up the coefficients of the terms where the exponents are similar or same. For instance, I don't have the term corresponding to exponent 4 in A, so this will go directly to my C, assuming C is my final. So I get 14x power 4. The next one is 3. Now I have terms here in A as well as B, so it becomes now 11x cube. 11x cube plus x square again I have, but now you can see here that plus 11 and minus 11, so it's 0x power 2. So whenever my addition becomes 0, I will not add the term. So I can just use a if statement in order to avoid adding a new term wherein the coefficient addition becomes 0. Next I have x, that is exponent is 1. I don't have any term, so I just write x. Now my constant term 9 plus 7, 16. So 14x power 4, 11x cube plus x plus 16 is my added value. That means a plus b. So when I do this, I'll be getting. So what I do, I'll maintain two pointers. Anyway, I have pointers to these nodes. So a and b. Now I will just compare the coefficients. See, first term here, this is 4, right? So obviously it is not same. So what do I do? See, remember, normally this will be in the descending order of the exponent values. So we will come to know that there is no x power 4 term in A, and only 3. So when the exponents are not equal, we cannot add, and we could actually put the term into the final linked list, that is C. I'll show you that in the code. And whenever the the exponents match, then we can employ addition, like 5 plus x cube and x cube here, 11x cube. So we will try to look for the similar kind of exponents, that means same value of exponents, and try to add them. And if the added value is 0, then we don't add that into the C or the final linked list, resultant linked list. Okay, so we will just see how this could be done using this. So C is my resultant added polynomial, and start A is a pointer which points to the first one. Star B is another pointer variable, local pointer variable, which points to the second polynomial. And this is a temporary variable which is used for adding some, to add the coefficients. So as usual, we'll create the dynamic memory for C and create a header node, you can see here. And in order to make sure, you can see that we have two more pointer variables A and B, local temporary variables, because this is not a normal singly linked list, in which case you will have null value as the last node next field. But we need to actually check this end of the node by seeing whether my A, because I'm going to use A for navigation or browsing through the list, and whether it has reached start A. So when I have the header node here, right, when I have the header node here, like this. So my last node, see, this is start A, right? So which will actually point to this header node start A, and A is actually going to browse through this, and when A reaches the last node, its link field actually points to. So I can compare A with start A. As long as they are not equal, then I can keep doing it. So in order to start scanning through my nodes, A is first initialized to link field of start A. That's what this choose. This is just to skip the header node and start from the actual node or the term. Similarly for B. Right. You can see here, as long as A is not equal to start A and as long as B is not equal to. See, another important aspect here is that, see, one polynomial may have 3 terms and another one could be 5 terms. So what happens here is that we cannot always think that number of terms will be equal. So one could be more compared to the other. For example, in this case, A is lesser than B, or it could be B lesser than A. So we don't know which one is going to get exhausted first. Now, once we get exhausted, for example, A will get exhausted first, and then we can copy down the remaining ones. Vice versa. That is also true for B. Okay, so if the exponent terms are equal, the exponent values are equal in both A and B, right? Then we can actually add this. Otherwise, we just copy. That's what I said earlier. So find out the sum and create a new node with C. Correct. Now, in our example, you can see that I take this and I take this. Is the coefficient same? Sorry, is the exponent same? No. So we'll be doing only when the exponents are same, then we will add the coefficients. Else, so which pointer variable is having the lesser value? So if A is having a lesser value, attach that other corresponding node. Otherwise, so whichever is less, you can see here, if A is less, we will attach B, and if B is less, we will attach A. So in our case, see, A is less, so we will attach B. So this term will go to C and we will not move this. So this pointer variable B will be advanced. So you can see here, B will be advanced accordingly, and here A will be advanced accordingly. So depending upon the larger one, the term, because we don't have a matching term, it will actually be added to the resultant linked list, which is called as your C. Now, this while loop will get broken if A has lesser number of nodes or B has lesser. So in our case, A has lesser number of nodes, so this will quickly be equal. That is A equal to start. So we will have some more terms in B which should be copied or otherwise. So there are scenarios where it could be the other way also. So it should work for both. Now in either case, supposing if A gets exhausted first, copy the remaining one from B and vice versa. So you can see here, if A is not equal to starting from remaining nodes from A, if it's not equal, remaining, you don't actually need to check whether it has reached start A or not. So this itself will actually take care. See, in our case, we have only 3 nodes, right? So this condition will be false. So we will be adding only B. Okay, it will be false. So this statement will not be executed at all. And only this will be executed. All the remaining from B will be copied into C. And suppose if B is lesser number of terms compared to A, then this will not be executed. This automatically will get executed because A will not be equal to start A. Okay, so the idea is that the remaining nodes from A or B should be copied to C. And C is ready now, you can return. So this is how we we first create the linked list by reading, and then we employ addition based upon exponent checking. If both are equal, sum it and then add. And if the sum is 0, we don't actually add. That's why you can see here if sum. So this condition is true only when greater than 0. So obviously 0 kind of sum we will not add. So it should be greater than 0. Right. So this once we construct the added polynomial, we will return the pointer variable of C which has this. Then we can display the entire list. So that I'll show you the full program in the code using Visual Studio. So this is my Visual Studio Code 2019 screen, and this is the simplest tool. In fact, is a lightweight tool, and it's a class platform. We can use this tool for IDE actually for any language. In fact, you can use Python, you can use HTML, you can use JavaScript, you can use C++. I mean, any number of languages it actually supports. But only thing is that you have to add appropriate extension. So this is the extension addition. So for executing C programs, you need to go to this and then look for example, here you can see code runner, run C, C++, Java. So you need to, install. You can see here code runner is there. Then we have, yeah, this is the actual compiler actually, C or Visual Studio Code. So since I've already installed, it shows my uninstall. If it is not installed already, then you will have whether to install. So you can install that. Now this also is required to run your code, which I'll show you. So this is my code here. This is my macro malloc in capital letters, which in turn uses malloc. Okay, so this is my structure, which has coefficient, exponent, etc., etc. And this is my global variable last. So this all we have seen already. And the main program now, I have 3 pointer variables of type node and initialize to null, and enter the first polynomial, that is read in the first polynomial, read in the second polynomial, then add these 2 polynomials and we get it in C, and resultant polynomial you can display. So that's a print statement which will display. So we need now functions for read C poly and cpad, cpadd. Okay. So this is my read polynomial, which I've already shown in the PPT. Attach is the function which attaches every node at the end, and this is the addition, polynomial addition, and display is simple display, and skipping my the header node, etc., and hence I get my resultant polynomial being printed. So now let us execute this and see. There is another important. So you can see here automatically it takes up this in order to make sure that it automatically gets executed under the terminal. We need this kind of setting to be done. Okay, now you can see here, enter the coefficient for the first polynomial. So the same example, that is the coefficient is 5 and exponent is 3, and next term is 11 and 2, and then we have 7 and 0, and so this is my last term, so I'll just conclude this, then go for B, 14, 4, then the second term is 6, 3, 6, 3, then the third one is minus 11 and 2, and then we have 1 and 1, and we have 9 and 0, so minus 1, minus 1. Yeah, now you can see the result, 14x power 4, correct, plus 11x cube, that's also correct, plus x and plus 16. So this is exactly what we have shown, the added uh, value for each term of the two polynomials.